today you're going to be learning about special right triangles. There are two types of special right triangles that we have to look at and learn and study the ratio for. The nice thing about special right triangles is that even though the relationship comes from Pythagorean theorem, if we can identify the triangle based on the angle measures, then we can use this ratio that we know is always going to hold true to help us calculate side lengths much faster than if we were using Pythagorean theorem. So the first type is a 45, 45, 90 triangle. What we want to think about here would be if we had a square and we created a diagonal. So the diagonal connects two opposite corners of a square. When we do that, we're going to make two isosceles triangles. In an isosceles triangle, the base angles are always going to be congruent, meaning that they have the same measure. And in this case, because we took a 90-degree angle and cut it in half, we're going to create two 45-degree angles in the corner. And so this picture on the left side of your screen would be an example of a 45, 45, 90 triangle that's basically half of a square if we think about visually expanding that out to be a square. And so that's the first type of special right triangle relationship that we're going to look at and study the relationship for. So the important thing that we always want to make sure that we think about when we're working with right triangles is that your hypotenuse is always the side that's opposite the 90-degree angle. It does not matter if they spin the triangle around and it looks different. You always want to make sure you visually line up and think about that the hypotenuse is opposite of your 90-degree angle. And because we have an isosceles triangle, when we have created this special type of triangle, these two other sides, we call those the legs, are going to be the same measure because all four sides of the square are congruent. And then we also know that we have two congruent angles in the corner, which are 45 degrees. So if we said that we were going to think about setting up Pythagorean theorem for this right triangle, we would say a squared plus b squared equals c squared, but because these two legs are the same measure, I can call them both x, so we would still say x squared plus x squared. That's going to be equal to the hypotenuse squared. So now we can start to solve this equation for the length of the hypotenuse. So we have 2x squareds over here on the left side equal to the hypotenuse squared. We can take the square root of both sides because that's going to cancel out the square root here and squared here. Now, the square root of 2, we know that that is an irrational number, but I can take and break apart those two values, and we know it's going to be equal to the hypotenuse. So if we can keep simplifying here, then what we're going to see happen is that I'm left with just x, which in this case is your short leg, times the square root of 2 equals the hypotenuse. That is always going to be true for every single 45, 45, 90 triangle. Your leg, we're going to call that x. It doesn't matter what the measure of that side is. Your hypotenuse is always going to be the length of that leg multiplied by radical 2. So that can be a little confusing until we start to actually see that in practice. So let's look at some examples of our 45, 45, 90 triangle. So again, because we're going to study another type in just a second, it's really important that when you look at these triangles, first that you identify the fact that we have 45 degrees. And we know that in a triangle, all the angle measures have to add up to 180. So if this one's in the bottom corner is 90 and I have 45, that means that this one up here at the top has to be 45 degrees as well. So we're looking at a 45, 45, 90 triangle. So we know that the two legs opposite the 45 degrees are going to be congruent. So these two sides would be the same. So we can set up and use our proportion. So we know that the hypotenuse is always going to be the length of the leg times radical 2. And then I'm going to take what I see in that triangle and start to fill in this ratio that we know always holds true. So the length of one leg is 8. So that means that the length of the other leg is 8. The length of the hypotenuse is always going to be the length of the short leg times 2. So all I have to do is plug in the length of the short leg for x, and I know that the last part is going to be 8 radical 2 for the length of the hypotenuse. Okay? So let's look at a slightly different example here. So again, we've taken and we've kind of turned this right triangle in a different orientation than what we're used to. So the first thing I want to look at is make sure I know what side of the triangle they've got labeled with a number. Well, that's opposite of the right angle, which means this side has to be the hypotenuse. Now, they haven't labeled any of your angles in this triangle. However, what they have shown me is that I have two sides that have the same measure, which tells me I have an isosceles triangle. So I have to be looking at and working with a 45, 45, 90 triangle. So what I don't know are the lengths of the short leg, but I do know that the hypotenuse is going to be equal to 5. Okay? So we have to kind of take and use the information that we're given and work backwards. So I know that this 5 is equal to this part of the ratio. It's going to be equal to whatever the short leg is multiplied by the square root of 2. So that's the equation that I want to set up and solve. So x radical 2 is equal to 5. To get x by itself, I would divide both sides of the equation by the square root of 2. So these are going to cancel. I'm left with x equals 5 over radical 2. Well, we know that mathematicians don't like for us to leave a radical in the denominator. So to rationalize the denominator, we multiply by whatever radicals in the denominator divided by itself. And then when I multiply fractions, I multiply the numerator together. 5 radical 2, I can't multiply the 5 and the radical 2 together because the 5 is not under the radical. So I can multiply them, but I just meant I can't write them both under the radical. So we would write it as 5 radical 2. And then your denominator would be the square root of 2 times the square root of 2, which is the square root of 4. And that's going to simplify to be the square root of, not the square root, just 2. So that is the length of x, or a leg of that 45, 45, 90 triangle. So one last example. Jana is cutting a square of material for a tablecloth. The table's diagonal is 36 inches. She wants the diagonal of the tablecloth to be an extra 10 inches so it will hang over the edges of the table. What size square should Jana cut to make the tablecloth? So we're going to start with our table. And once we have the table drawn, we're going to draw in our diagonal of 36 inches. She wants the diagonal of the tablecloth to be an extra 10 inches so that it will hang over the edges of the table. What size square should Jana cut to make the tablecloth? So she actually wants to take and add 5 inches on each side because we want it to stay congruent and still be a square. So 5 and 5. And that's going to give us our new tablecloth dimension so that it actually hangs off the edge of the table. And we need to find these dimensions here, x and x. So her total diagonal now is going to be 46 inches because we've added 10 inches on both sides. And because we had a square, we know that we took and we cut these corners into congruent angles. So now we have a 45, 45, 90 triangle that we can use to help us find the other two sides of that square. So we go back to our ratio for a 45, 45, 90. What we have is the hypotenuse of that right triangle, the diagonal of that square, so 46, which means that I'm taking these two parts of that ratio and setting them equal to each other so that I can solve for x. So again, we're going to divide by radical 2 so that they'll cancel here. I need to rationalize the denominator the same way we did on the last problem. So I'm going to have 46 radical 2 over 2. The last thing that we want to check is that we can simplify this fraction in the front if it can be simplified. And 46 divided by 2 is 23. So 23 radical 2 would be the side lengths of that square. Now, if you'll notice here, directions say to round to the nearest inch. So when it has the radical, that's an exact answer. But sometimes we do need to take and multiply and get a decimal answer. So I'm just going to take my calculator here, because radical 2 is actually an irrational number, meaning that we can't actually take and measure exactly radical 2, so we're going to have to approximate, and it's going to be 32.5 inches as our final answer. The other type of special right triangle is a 30, 60, 90 triangle. If we were going to take and prove the relationship for a 30, 60, 90, we would use an equilateral triangle. So if you remember from your studies before, equilateral means that they have the same side lengths and the same angle measures. So an equilateral triangle has 60-degree angles at all of the vertices, and then all of these side lengths would be the same measure. Now we only have half of our 30, 60, 90 triangle here. So because when we started with the equilateral triangle, this side here would actually be the entire length of the hypotenuse of that right triangle, because of the properties of the equilateral triangle. When I took and cut half of this away, I now know that the remaining side is going to be half of what the length of the hypotenuse is. If we took this and we used Pythagorean theorem and set up and solved, what we would see is that the other leg is going to be square root of 3 times the length of this other leg. Now, for sake of time, I'm not going to go through that whole proof with you. One thing we do want to think about, though, is when you have a 30, 60, 90 triangle, you have what we refer to as the longer leg and the short leg. And you see that labeled here on the picture. Now, we know which one is the shorter leg because it's always going to be across the triangle from the 30-degree angle. Okay? And this goes into some more properties with geometry that we haven't studied here. But there is a relationship between the angle measure and the length of the leg in the triangle. So the longer leg, because it's across from a larger angle measure, 60 degrees is larger than 30, we refer to that one in this type of triangle as the longer leg. And then we said for every single right triangle, anything that's across from the 90-degree angle is our hypotenuse. Okay, so how does all of that work together? And we have this idea of a ratio. So the short leg is what we're going to call x. It's just kind of our given relationship. Now, we said that we did know that that was going to be half the length of the hypotenuse. We're actually going to take that relationship in reverse. We're going to say that we know that our hypotenuse is always going to be 2 times the length of the short leg. In our right triangle. And then our longer leg is always going to be the length of the shorter leg multiplied by radical 3. So short leg, long leg, hypotenuse. The short leg is our kind of base measure. The hypotenuse is always going to be twice that measure. The longer leg is always going to be the length of the shorter leg times radical 3. This is really one of those skills in math that you just have to keep practicing. And then once you understand it, then it starts to come much easier. So again, you just want to make sure that you probably practice this on a couple different activities just so that you reinforce the skill. So looking at this triangle, I know that this one is a 30, 60, 90. I can see that from the angles that are labeled on the triangle. So again, we have to look at sides opposite. So opposite the 30 degrees, they have that labeled X. So that's going to be our short leg. I'm going to go ahead and write this. So again, this is short leg, long leg, hypotenuse. Okay, so short leg in this triangle is labeled as X. The long leg, which is opposite of 60, is 15. And the hypotenuse in this is labeled Y. So even though they give us one side, I can actually find all 3 measures of this triangle. So the only side length I know is 15, and I know that it is the length of the short leg times radical 3. So I can use that to help me solve that equation. So I take those 2 things because I know that they're equal and set them up and solve for x. So I would divide by the square root of 3. Again, I don't want that radical in the denominator, so to rationalize, I take whatever radicals in the denominator divided by itself. So the numerator becomes 15 radical 3 over the square root of 3 times the square root of 3 is the square root of 9, which is just 3. I want to check the numbers in the front. So 15 divided by 3 is going to simplify to be 5 radical 3. That is equal to x, which in this triangle is what we refer to as the short leg. And we know that the hypotenuse is always going to be 2 times that, so 5 times 2 is 10. And we leave the radical 3. And that would be my 2 missing sides in that triangle. In the next example, they only give us one measure, but again, I know that these have to add up to 180, which means that has to be a 60-degree angle. So 30, 60, 90, short leg, long leg, hypotenuse, x radical 3, 2x. The short leg is opposite 30, so that's 5. The 60 degree is opposite of x, so I don't know what that one is. And I also don't know what the hypotenuse is. They just have called that y. So it can get a little confusing because we use x in the ratio, so just be careful with that. I'm just writing that there so I know what it is I'm solving for. The only thing that I can work with here is this first one because the other two I haven't been able to solve. So I know that the short leg is 5. Well, the easy thing here is that the hypotenuse is always going to be twice that length. So 2 times 5 is 10. And the long leg is always going to be whatever the length of the short leg is times radical 3. And we're done. And I just wrote a 2 instead of a 5, so I'm going to fix that really quickly. That should be a 5 because that was the length of the short leg times radical 3. So those would be my 2 answers. So this one would be 5 radical 3 is going to be the long leg, which in that one is labeled as x. And the hypotenuse was labeled as y, just to make sure that we remember what was what. So 30, 60, 90 does take a little bit of work because those 2 legs, the shorter and the longer legs, are going to have different measures. Alright, so the last example says the altitude of an equilateral triangle is 18 meters. Find the perimeter of the triangle. So we're going to start by drawing in a picture. So here's my equilateral triangle. I know that these are 60 degrees. The altitude is another word for height. So the height of a triangle has to be formed by a 90-degree angle. And in an equilateral triangle, your altitude is always inside. And so they tell me that this has a height of 18. So I know that I'm working with 2 30, 60, 90 triangles inside of that equilateral triangle, which now will let me solve for the side length of the triangle, which is what I need in order to find the perimeter. So again, we want to think about what is it that we know. Well, we know that we have the long leg of that triangle is equal to 18. That's the length. And in our ratio for a 30, 60, 90, the long leg is always equal to the short leg times the square root of 3. So we would divide by radical 3, divide by radical 3, so this cancels. Again, I do not want a radical in the denominator, so I'm going to have to rationalize and multiply by radical 3 over radical 3, which would be 18 radical 3 over 3, and 18 divided by 3 is 6. So I have 6 radical 3. Now what we have to be careful about is I didn't actually solve for the side of that triangle. I solved for the side opposite 30, which is down here. So that's 6 radical 3. So I have to double that to get one side of that equilateral triangle. So a whole side length of that triangle is 12 radical 3. So to find the perimeter, We have 3 of those sides. So we can either add it 3 times or we can just think about multiplying it by 3. And 12 times 3 is 36. And we would leave it as radical 3. And so this is in meters as our unit. So that's everything for our 2 types of special right triangles. Again, make sure you identify which of the 2 it is. Make sure that you know what side it is that you've solved for, especially in the 30, 60, 90, by looking at where you're at in the triangle and what is opposite each side.